what kind of measurement error would motivate the use of an SEM? Like just a very basic example from your field.
We use a lot of questionnaires. So, for example, for measuring depression, so people get asked questions and they may just simply misunderstand the question, or it may not be clearly worded. Sometimes questionnaire items are kind of two parts. So, for example, like an item could be like, I feel depressed and sad all the time. And then maybe people are unsure. Well, yeah, I kind of feel sad, but I don't know, is that depressed? So they're like unsure. Does both of them apply to them? And so also when the data is being entered into a database and numerically coded, people might make errors entering the data. And so there's typically random noise associated with questionnaire items and also test items. So when you have an intelligence test, and a capable student may randomly make an error with a number series problem, even though they're capable enough to solve that item, but they just may randomly make a mistake. And so we have a lot of that. It's unlike physiological measures, like when you measure temperature, it tends to be more precise than measurement in the social sciences, where people have to read questions and answer to questions. And
Yeah, because like in biology, like I work a lot with biologists. I mean, there is variability in measurement, right? So if I measure, I don't know, blood pressure 3 different times, I won't get maybe exactly the same reading, but I think in social science or in the field like psychology, when you say like depression, I want to measure depression, like what does that really mean? Like to operationalize that variable and create a measurement scale for it is a whole process, I think, and the measurement itself has to be taken into account in the statistical analysis, and I think that's kind of what you're saying, right?
yeah, so there are different aspects to reliability and validity. So typically in measurement theory, so what we use oftentimes in psychology is classical test theory, where measurement error is clearly defined, so to say, as random noise. So you have a true score, person's true score. So if you could measure individuals' ability an infinite number of times with the same test, then there would be a distribution of the scores simply due to random noise. Not every measurement would be the same, and so you could just take the mean of that distribution. That would be the true score, so the best guess of that person's ability. And so then deviations from the true score, that's what's defined as measurement error. So that's one aspect that can be modeled in structural equation models, is random measurement error in the sense of classical test theory. And then also invalidity. So there's this issue of method effects, for example, like you mentioned, rater effects. When you have self-reports and other reports, they may not agree. So where is the true depression? Is it the self-report, or is it the other report that is better able to capture that? And so that can also be modeled with structural equation models that include multiple rater data, where we can look at convergent validity between different raters and model method effects as well. And so there are all these sources of systematic and unsystematic error that maybe in other sciences don't exist, where it just is in physics, it's just pretty clear what you're measuring. In psychology, it's not always so clear what you're measuring. And so therefore, psychologists are so concerned with reliability and validity. And so confirmatory factor analysis and structural equation modeling offer ways to address that by using multiple indicators. So multiple items, which basically is for repeated measurement. So like you mentioned earlier, so in order to determine reliability, we need to measure the same thing multiple times. And so oftentimes we do this with multiple items or multiple tests, and then we can determine to which extent those different items or tests share the same variance, so to which extent they're correlated. And so that's then what allows us to define a latent variable. And so the higher the correlation between the measurements, the more reliable those measurements would be, and the more variance in the latent variable, meaning the more true score variance. And so the goal is to separate, first of all, true score variance, so reliable variance, from measurement error variance. And then the structural equation model works with the true score variance in the latent variable and uses that then to relate that latent variable to other variables, so that the coefficients, the path coefficients or regression coefficients among the latent variables are less biased than would be the coefficients if they were estimated between manifest or observed variables that are not corrected for measurement error. So a latent variable is basically a perfectly reliable version of the observed variable.